And you're very welcome back. The second part of a statistics video, it might be your first part if you haven't watched the first part, you felt like you had that covered. Or even if you watched the first 5 minutes and went, gotcha, remembered, it's all in the notes here in front of me. In this part, we're going to look at how we present data in tables and tallies. So we've already done some tallies, but I'm going to give you some more tips and tricks for doing tallies just in case you need it, and then show the difference between tallying discrete and continuous data and group data. We will then go on and look at some stem and leaf diagrams and see how we might display those as well. Okay, so if we jump right into an example here, we'll look at one of the rather confusing ones. So here are the vowels from the first three sentences of a book. So somebody's written all these vowels out, and as you can see, it can be difficult to ascertain which one's the most popular from that group, just by looking at the way it is. So we would need to put the results into a frequency table, sometimes called a frequency distribution. And the best way to do this is to draw yourself a little table and then tally them. So I would do A, whoops, E, I, O, U. And the trick is that you would go through each letter and stroke it off. So you would do, there's one E, and start your tally. There's one A, start your tally. One E, start your tally. U, start your tally. I, etc., etc. Now I could go the whole way through this. There's a couple of points I want to make about it though. When you're doing your stroking off, do it in pencil. If you make a Horlicks of it and you've done it in pen, it can be very hard to rectify. You want to write all your other answers in pen on the paper, but this one you want to mark them off in pencil, because then you can rub them out and start again if you realise. You do a quick count. When you do a count, you'll have 1, 2, 3. You'll realise that there's 20 in a row there, and there's 3 rows of 20. So there are 60 altogether. And if when you're doing your count of your tallies here, your total should add up to 60. Now, in good Blue Peter style, here's one I prepared earlier. And there's actually the answers. So you can see the vowel for each, A, E, I, O, U, the tally for each, and then the frequency, which is the number of each vowel that there were. Tallies, like before, are grouped in fives, or the 5 gate, to make them easier to count. And if you add the frequencies together, you'll get the total number, which is 60. Which again, if you haven't got 60, you know you've made a bit of a boo somewhere. You'll have to go back to the start again. There's kind of no other way around it. If I put it in this kind of table, it's easy to see that E is the most popular vowel. They're followed by A, followed by I, followed by followed by U. Dead easy. What type of data is this? It's discrete data because it's counted. We're counting the number of vowels that have appeared. Okay, so again we'll touch on group data again, similar to the example before, but because the results are so widespread, we might decide to group the data to make it easier to analyze. Be careful that all groups are the same size and that there is no overlap, and make sure all values are covered. So same size, no overlap, make sure all values are covered. Let's look at another example. In a quiz, there are 40 questions, each worth 1 mark. These are the scores of the 30 people who entered the quiz, and there's your results. Now, you could make a table with 14, 15, and see the number of occurrences, but in this case, that table would be very, very big and might be overly complicated. So what we'd like to do is group the data together, and it says the groups must overlap on the right. Let's get my wee highlighter out. Yep, here we go. So the groups must overlap. Choose intervals that are suitable. So they've got 11 to 15, 16 to 20, and as you'll see, the interval for those is 4. And they're called class intervals, or the classes. We did discuss that some last year, but I'm going to start using the terminology more and more this year. The 11 to 15, 16 to 20 are called class intervals. Okay, so if I show you what that looks like in the table, you see here. So we get our first one is 11 to 15. Then we've got our 16 to 20, 21 to 25, 26 to 30, 31 to 35, and 34 to 36 to 40. You'll see that they're all exactly the same width. They all encompass 5 marks. I know you're probably saying there's a difference of 4, but they encompass 5 marks. The 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, etc., etc. So they're taking 5 marks. And you would do exactly the same thing as you did before. You would go to 23, and you would see which colour it goes into. You would put your mark down there, and you would score it off. Do the same for 14. Do the same for 17. And eventually, you would end up with these results. Okay, so after the scores are discrete and can be grouped, like I said. So after the table's been put in the frequency table, you can identify individual scores. You can't identify individual scores unless you look back at the original data, but you can see roughly what was the most popular mark. And the most popular marks fell between 26 and 30. There was more of those than any other group. Probably not surprising. There was, one person that scored very, very low, and a couple of people that scored very high, and this big swathe around the middle was where most of the results came. So there's a couple of things we can draw from that, but again, we're not going to really look very much past that. Okay. Next bit. I'm going to throw a higher level alert here. So again, that was continuous data. If I look back, these scores are counted. The number in the scores is counted. You either scored 23, 24, 25, 26, 27, 28, etc., etc. What happens if you have continuous data? What if the data is measured? Now, remember, if we look back to what we were trying to cover beforehand, we want to make sure there's no overlap and to make sure all values are covered. So if you're measuring somebody, if I'm measuring the height, for instance, I could measure, God, I don't even know what I measure height-wise, but let's say I measure 174 centimeters, roughly. Well, and somebody else could measure me more exactly, and I could measure 173.94 centimeters. This would cause a problem, because if I'm doing my ranges between, say, 170 to 173, and then 174 to 177, if I'm 173.94, which of those two groups would I fall into? Well, the answer is neither, because that one ends at 173.0 and this one starts at 174.0. So there's a gap of 1 between the two. What do we do to get round it? Well, I'll show you what we do. I wouldn't leave you hanging like that. What we do is this: we use this notation. So if we were measuring people's heights in centimeters, we would use, I'll just get my highlighter out, we will use this one first. Oops. That one means less than or equal to. And if I do that, I'll do less than or equal to. This one here just means less than. So we'll investigate what this means. H is your height. So the height for the person that we're talking about here that scored 1 was either, if you see where it ends to, even though that sign is less than or equal to, this says that 180 is less than or equal to H. So this means that H, and this bit can get quite confusing, is either 180 or greater. And this means that H is also less than 190. Again, what's the difference? Well, this includes 180. This does not include 190. It can be 189.9999999 as far as measuring goes, but as soon as it hits 190, it falls down to this next category. So you are covering all of the ranges of heights. So it doesn't matter how big or small your decimal value is, you are going from 180, the whole number, up to the 189.9999999. This one's 190 to 199.999999, and anything that falls in between. So you're always covering everything that's in there. Now, I'm going to take these couple of bits away for the moment so that we don't get too confused. So 210, if for instance, if that was a height, would fall into this one here. 210 to that one. 220 would fall into that one. And 209.99 would fall into that one. So if I just write those in, that one's there, 210 goes in there, 220 goes in that one, and 209.95 or something like that will fall in there. Okie dokie. So one of the skills in the higher papers accepted that they do, they could ask you to design the class intervals. And what you have to decide is your data discrete or continuous. And if your data is discrete, you will have a table that runs something like this. You will have something like, 16 to 20. They will be whole numbers. 26 to 30. And that will be discrete. So if that doesn't look like a less than or greater than sign or anything, I'll put an arrow through it. That's discrete because everything will have a definite value. There will actually be 16, 17, 18, 19, 20 of something. There will not be any decimal points in between. If it's continuous, you're going to have to design your ranges like this. And that's continuous, or data that's measured. Now, we will do some examples of this when we get into class, but that's the key thing to realize, that there's a very definite difference. Okay? And that's part of your higher level stuff that's there. Okay, time to move on. We'll not do a worked example of that yet because, again, it's all very theoretical and it'll come up later as we go through some of the later questions and we will get recapping it, etc. I'll do two white tables. So data that covers multiple instances of stuff, such as the eye colour of boys and girls in a particular class or year group, needs to be presented in a way that makes it easier to answer simple questions or to pull. Rather than have two separate tables, you'll have one table, and we call these two-way tables. It shows how eye colour and gender are related. So, if I go to, say, this cell here, this will contain the number of students that are boys and have blue eyes. So, say that was 4. This one will have the number that are girls and have blue eyes. Say it was 6. Oops. The boys that are brown eyes, say 2 and 3, and in the eye colour there's 1 and 3, something like that. Say there's 3 green eyed girls or something, right? What we could do from this table, there's a couple of things we can do. Obviously, you'll be able to pull the information out about each individual category. So if a boy has got blue eyes, there'll be 4. If a girl has brown eyes, it'll be 3. But if I asked you for the total number of boys, well, you would look up at the total along this row. So you'd add up all the boys. So you'd look at the starting point, which is over here, and you would add up the whole way across, and you would get that there are 7 boys. If I asked you for the number of girls, you'd find out there were 12 girls. In fact, the question could ask you straight off the bat, how many people were there in the class? And if you get to one end, you will see 7 plus 12. It doesn't give you 21, by the way. I don't know what I was thinking. It gives you something completely different from 21. It gives you 19. 19 people in the class. And there's another way you can check, actually. Because if I asked you for the number of people that had blue eyes, I'd add the 6 and the 4 together and I'd get 10. Brown eyes, there are 5. And other eye colour, there are 4, 1 plus 3. And doesn't matter which way you add them up. If you add up the numbers in that row or that column, it should be the same. So let's look at an example. We're going to look at this two-way table. So the two-way table shows the eye color and gender of students in Mr. Jameer's tutor group. And in this example, they've included the totals for the rows and the columns. So we'll just pull some information from this. Okay. First question is, how many girls have blue eyes? So we're looking at the row with girls along here, and we're looking at ones with blue eyes, and that number is 7. 7 girls have blue eyes. Brilliant. How many boys have neither blue nor brown eyes? So if they've neither blue, there's the boys row there. There's 3 have blue, there's 8 have brown. The only other option we've got is another eye colour. And how many have neither of those? Well, that is 2 according to the table. Okay. How many students have brown eyes? So it's looking for the total of people that have brown eyes. There's your column of brown eyes. 8 boys, 6 girls, for a total of 14 altogether. And how many students are there altogether in the tutor group? Well, there's 13 boys and 18 girls, and this spot down the bottom right gives us it. So 13 and 18 gives us 31. That is there and there. Nice and easy. Okay, this is all very good. So that's two-way tables. We're going to move on to stem leaf diagrams. And stem leaf diagrams are an alternate way of displaying large quantities of data rather than grouping. Now, they're not suitable for large data sets, and you'll see why. It is best shown with an example, but I'll explain a little bit first why they're not suitable for large data sets. If I flick back to when we were doing our group data like this, when we were doing these, we didn't keep the essence of the original data, so we didn't know where the spread of the three values were between 190 and 200 when we did this method. We just knew they fell within that scope, so they could have all been like 190 rather than evenly spread. In a stem and leaf diagram, we can capture that information. Okay, so it's a good way of displaying that data if you want to keep that bit of information, but because we keep into each individual set of data, it's not good for really large data sets. Okay, so let's look at an example of these stem and leaf diagrams. So a maths test is marked out of 50, and here are the scores. So you have 27, 28, 36, 42, etc, etc. And it asks you to do two things with it. It asks you to draw an ordered stem and leaf diagram to represent the data, and it asks you how many students had a maths score of less than 20. Well, you can actually answer the second one just by observing the data, but we're going to show how you would do it using a stem and leaf diagram. Okay, so I'm going to move on to this little workspace here to make it easier to see, and there's a couple of things that I'm going to start off with that we need to really define or set out. Okay, so the first one is we're going to look to see what the smallest value that we'll have in the list. And so if I scan across and look, I'll see that along the top line the smallest value you can see is 18, and then on the next line, oh, there's a value of 7. So the smallest value I have is 7. What's the biggest value? The biggest value, if I look across, is 50 in the top line, and the bottom line there's no bigger, so the biggest value is 50. Okay, and that's our start. Now there's one other thing we need for every stem leaf diagram. Much like a pictogram or anything like that, we need a key. And what we'd say for the key, if you just look, is 2 bar 7 stands for 27. What does 2 bar 7 mean? Well, it means that if I write 2 here, whoops, this bar stands for the bar in the key. So 2 bar 7, and I write 7 the other side here, stands for 27. What I'll also do is fill the other bits in. Whoops. No, 1, 2, 3, 4, 5. And what that means is that there are numbers with no 10s all the way up to numbers with 5 10s in it, and we're going to list them all in our table. So the way we do this, and I'm going to change color, is that for each number that we go across, we just put it in the table. So 27, I'm going to stroke out, I'm going to put the 27 in as a 7 there. 28 goes in. It goes in like that. 36 goes down to the 3 and the 6. 42, etc., etc. So I think you get the idea. So I'll start running through this a bit quicker so that we don't get bogged down in the minutiae of it. And if I make a mistake, I will have a look and see what we did wrong, or a way to check it in a minute. 29, 31, or 49, sorry, 31. And that gives us the first line done. Second line. We have a 33, we have a 27, a 37, a 25, a 47, a 40. And 7 is just written as not 7, so no 10s and 7 units. 31's like that, etc. Oops. Just like that. And I'll stroke the rest out. Now I went a wee bit quicker because I'm using this tablet pen. But that is our stem and leaf diagram. Now what it is a stem and leaf diagram, and what it's not is an ordered stem and leaf diagram, and the two are very, very similar. A stem and leaf diagram that's ordered looks pretty much the same. I'm going to reverse my colours around. Not 1, 2, 3, 4, 5. I'm going to change my colours around, and all we do is write these numbers in order from smallest to biggest. So the 7 and the 9 aren't going to change, and neither is the 8 because that's the only number there is there. But if I look at the 20s row here, there are 3 5s. So I've got 1, 2, 3. Then we'll have a 6, 2 7s, and an 8. Make sure I've got the right numbers here to make sure I haven't missed one. So there's 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4, 5, 6, 7. Okay, that's that one. And the row with the 30s, we have 1, 2, 3 1s, a 3, 2 6s, a 7, and a 9. In the 4s, we'll have a 0, 2, 2, 7, 9, and 1 in the 50s. One last check I'm going to make. I'm going to add up the totals in the corners. So there's 2 in there, there's 1 in there, there are 7 there, 8, 5, and 1. And if I add this up, 2 plus 1 is 3, 3 plus 7 is 10, 10 plus 8 is 18, 18 plus 5 is 23, and 23 plus 1 is 24. And sure enough, if I check, there are 24 numbers to start with. So the chances are that we've accounted for them all, and we are right. Now, we can move on to the question. Like I said, we can answer it without looking at the diagram, but how many students had a math score of less than 20? Well, because it's ordered, we can see that the smallest number in the 20s was 25. So anything lower than that is going to be part of the number that we'll want. So that number, and that number are all valid answers for what we're looking for. So it's just score less than 20. There are 3, which is fab. Okay, so that's an ordered stem leaf diagram on the right. The one on the left is the one that you need to go through in order to put it in order first. So you do the unordered one first, then order it, and then you can answer whatever question you've got. So let's do another example. Now, I've changed this a little bit for you so you can make a start on it. So it can also be used to represent data with decimals. And there are amounts that some students spent on lunch. There's the amounts there, £2.15, £1.73, etc., etc. And once you draw a stem leaf diagram for this data, I've indicated that I want it ordered because I don't see what use an unordered stem leaf diagram would really be in the big scheme of things. And I also want to find out how many students spent more than £2.50. Now, the challenge is, if you want to stop the video and try and do this one yourself, you can. Otherwise, you can follow along with me. Alright, the bit that I've given you is that 2 bar 15 in this case stands for £2.15. So you can give it a go. If you don't feel brave enough, you can stop, and I'll have a look here and see what way this works out. So if I look at this question, I'm going to do exactly the same steps as I did beforehand. Okay, so our biggest value is, looking across, oh wow, look at there, it's £2.81. And our smallest value, if I look across, is 76p. So I've already given you that the key is 2 bar 15 equals £2.15. So my smallest price starts with no pounds and it goes up to £2 something. Okay. And then I will work through it. So I'm going to change my colour so make it stand out. £2.15 goes, I guess, 2.15. Stroke it off. £1.73. Stroke it off. 63. Stroke it off. 76p. Lovely. £2.46. £2.71. £2.62. £1.70. Whoa, that's not right. Let's gas that bit there. Didn't write that right at all. £1.70 looks like this. Not £1.17. 82p looks like that. £2.81 looks like that. £2.53 looks like that. And you've £1.62. So you have £2.62 and £1.62. And like I said before, you want to check to see if you've got all your values. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there are 2 rows of 6 up above. So that is indeed all the values accounted for. Okay, so we'll order this now. And the first row is indeed in order. So it's 76 and then 82. To put this in order, it'll go 62, 63, 70, 73. Okay. And then down here, we'll go 15. Next biggest is 15, 46, 53, 62, 71, and 81. And that's our ordered Stemleaf diagram. If I look to see how many students spent more than £2.50, well, £2.46 is that one. Anything above that is going to be big enough for you. So that's 1, 2, 3, 4. And that's that. So there are 4 students that spent more than £2.50, which is all good. Okay, we're going to move on to scatter diagrams. Okay, scatter diagrams are powerful ways to spot trends in data which needs to be which has been collected and not analysed, and you'll need graph paper for these. Okay, so where do scatter diagrams come into play? So say you've collected a whole load of data and you want to see is there any correlation between the data. You would use a scatter diagram in order to plot these two things against each other and then see if there's any trends. So the best way to really do this is to look at an example. Okay, so here's our worked example. The table below shows the exam results in maths and science for 15 students. We've got to draw a scatter diagram for this data, plot the maths mark along the horizontal x-axis and the science mark along the vertical y-axis, and describe the relationship between the maths and science marks. So it tells you in the right here to tick off the pairs of data as you plot the points, which is all fabby-dozy. Okay, so I'm going to use 2 colours. I'm going to use yellow as the colour for my maths mark, and for the science mark I'm going to use green. Not that this will actually show in the graph, but it helps separate the two. Okay, so what I'll do is I'll flick back and forwards here and then look at each of the points. So I'm going to pick a pair to start with. So something that's nice and simple like this one, 50 and 74. So a sans mark of 50 and a maths mark of 74. And what you'll see is the scatter diagram looks a little like this. Now it looks like an awful lot of other graphs that we've done. Exam results and some maths and science is your title, goes along the top. In fact, I'll take that bit off as well. That goes along the top. Up the side and the vertical goes the science mark, and across on the horizontal goes the maths mark. Just like they said. The other thing to notice that might throw you a little bit is this little boy here. Some people were very confident about using this last year, but this just says that nearly 1, 2 skip a few. We're leaving out the start of it, not 10, 20, and we're just starting at 20. Why says you, why are you allowed to do that? But in this case, the marks for the maths only start at 40. And if you're starting it at naught, you'll have a big portion of the graph that's going to be blank and not used. So why not spread it out or make it more visible by only including part of the graph? So I want to spread it out, so we're going to start there so that we get a good portion of the graph that's been able to fill in. So if we look at this, we were looking at the sans mark of 40, so we'll go along that line there, okay, to there, because that is where the 74 comes from here, and where those 2 points meet is this one. Now sometimes they're marked with an X, sometimes with a big dot, something like that, more usually an X, but you can decide which way looks best. Your neatness will determine what's best, but usually an X, a small X. And you'll do that for each of the points. Now, you can see the answer down there below, but the question asks, describe the relationship between the maths and science marks. And it says the scatter diagram suggests that the higher the maths mark, the higher the science mark. And that is true. So the person who scored the highest in the maths also scored the highest in science. In fact, the person who scored next highest in maths and the next highest both finished in that order. It's all good. It goes a bit screwy after that, but not a great deal. And in fact, the shape of this graph tells us an awful lot. What I'll get you to do in class when we practice it is this. We will get you'll try and draw a straight line through these points, and you'll try and get an equal number of points above and below the line. It doesn't have to be completely exact, but that's what you're going to try and do. And to be perfectly honest, I always liked that bit because it was like a little challenge to see if you could do it, if you could work it out exactly, or fit a line that goes around it. And that's roughly what it looks like there. We've got 1, 2, 3, 4 points below the line, fully above the line. We've got 4 above the line. It's not bad. It's not bad for me just looking doing this. Again, years and years of practice goes into this kind of stuff. But what we can say is that the graph looks like it slopes up to the right. Probably look at that if you're looking at me in reverse, but whatever. It slopes up to the right, and that tells us something. It tells us that it fits this pattern here, which is called a positive correlation. So it says on a scatter diagram, a line of best fit is a straight line that passes through the data with an approximately equal number of points on either side of the line. If a line of best fit can be drawn, then we can form some sort of linear correlation between the two sets of data. So if it slopes up to the right, we call that a positive correlation. As one quantity increases, the other one tends to increase. So as the maths mark gets bigger, the science mark gets bigger, or as people's weight increases, their height generally increases. Probably the best way is to say that way around. The taller people are, the heavier they are. We can also have things like a negative correlation. So it slopes down to the right, one quantity gets bigger, the other one decreases. So something like car value, the older it gets. The price of the car goes down, the older that it gets. Or battery life. The more longer a battery is running for, the less battery life it has. Okay. The other correlation you can have is that there is no correlation. The points are just scattered around randomly like they are here. Okay. And that can be something like, you know, hand span. If you're testing whether a hand span has a correlation on test results, so you're looking to see if the bigger the hand span, the bigger the test result. In this case, there is no correlation, and let's just say there is no correlation between any of these, and that's the key word, his correlation, should I say? All right, that one there. So you want to get that in your head, and we'll do lots of examples in those in class. And that's the end of the video today. I hope you enjoyed it. Any questions you've got, bring with you. There's a couple of quiz questions on data cycle and questioning, etc. down below there. You can give them a go, pop me the answers, we'll run through them in class. Alright, until next time. See you later. Bye.